Hello guys, and welcome again to comprehensive computer science course with Python. Let us have our introduction to computer science. So what is computer science? Computer science refers to the systematic study of computation, information processing, and automated systems. So computer science has several definitions, but today we are going to use this one. So it encompasses both theoretical foundations and practical applications across multiple domains. And let us have some historical timeline about computer science. So in 1837, Charles Babbage designed the analytical engine of a computer. 1936, Alan Turing formalizes the computation with the Turing machine. 1945, we have von Neumann architecture being established. 1957, we had Fortran becoming the first high-level programming language. Moving on, in around 1969, we had Unix operating system, which was developed at Bell Labs, and in 1989, we have Tim Berners-Lee, who invented now the World Wide Web, and 1991, Python 0.9.0 being released by Guido von Rossum, and 2006 we have Amazon Web Services being launched or launching cloud computing services, and 2012 deep learning revolution begins. And we can look at modern applications of computer science or CS. Number one of application of computer science is web development. And now, because we're depending on Python, so Django, Flask, Fast API will be the choice. And data science, we have Pandas, NumPy, SciPy, Matplotlib, among other libraries. And machine learning, we have TensorFlow, PyTorch, Scikit-learn, among others. Remember, we have module on machine learning, about module 12, so you can learn it. And cybersecurity, number 5, which entails cryptography, ethical hacking, among others. So the next module, on module 13, will be about ethical hacking and cryptography. And module number 14 will entail blockchain. So watch our videos, watch our modules to the end. And we also look at smart contract, Web3, and also computer science is also applied in scientific computing using BioPython and AstroPython. So let us move ahead on section 1, which will entail Python programming fundamentals. And section 1.1, we are going to look at the core language features of Python. So Python, first of all, let us define it. Python is an interpreted, high-level, general-purpose programming language, and it's known for its readability and simplicity through dynamic typing, automatic memory management, extensive standard library, multiple programming paradigms such as object-oriented programming, functional programming, procedural programming, among others. And let us look at basic syntax examples that we're using word root operator, and it was introduced in Python 3.8 and above. So for example, if count colon is equal to len hello greater than 3, so we need to print count characters. So we need to, this one will, the expected output will be string has 5 characters. So remember, this is a crash course, so I'm going very fast. So let me run code, and I will have to explain what is happening behind the hood. Py cs.py and hit enter. So you realize that a string has five characters. So we say that if count colon is equals to len and into parentheses we pass on hello is greater than 3, then we need to print using f string that string has count. So count is a placeholder that depending on the value that the user provides, and these characters. So hello, if we can count it, you have 0, 1, 2, 3, 4, and 5. So if we change another name like for example hello, and if I run, so you expect to get like 6 characters. So exactly, this is what the program gives us, 6 characters. Now let us have explanation of what has just happened using the Walrus operator. Colon is equal to assignment as value to a variable, so as part of an expression. So here we calculate the length of the string, that is hello, and assign it to a count within the if condition. So let us look at type hints, which was introduced in Python 3.5 and above. So let us define a greet function with the name colon star or string and given an arrow star, and we need to return the name. So let us explain first. Type hints specify the expected data types for functional or function arguments and return the values. So name colon star simply means name should be a string, and the arrow star simply means the function is expected to return a string. So let us print greet world, and the expected output will be hello world. Let me print the result in VS Code. I'm in VS Code and let me run py.py and I hit enter. So we have hello comma world. So the first is hello, of which we defined, and then we have a name placeholder that is in this our greet function. Hello guys, if we try to change this value from a world, for example, to value to an integer value, like for example 76, and if I print the result, you realize that it will say hello 76, but that one does not mean anything meaningful. So 76, it will be converted to a string by default because the program is expecting a string. However, there is a way we can introduce try and catch error, such that the only value that is expected as a placeholder should be a string and not a number. So any number will not be accepted. So I hope in future we are going to use that try and catch statement. And now in this section we are going to look at structural pattern matching using Python 3.10 plus or Python 3.10 plus. And let us have our describe number function with num argument and match a num and case 0. If you have case 0, then you have to return 0. So if the number is exactly 0, then you have to return the it as 0. And case n, if n is greater than 0, we need to return the number is positive. So this one simply means if num is greater than 0. And case underscore, which will be our default, we need to return negative. So this underscore is the default case for anything else that the user will provide. And match is similar to switch case in other languages, and it also allows checking a value against patterns. It matches the value of num against several cases, and if we print describe num and we pass on 5 as argument, the expected output will be positive since 5 is greater than 0. Now guys, this is our function in VS Code, and now it's time to run and validate our output. So pi, I can type way pi, okay, pi cs.py, and I hit enter. Then you realize the number is positive, the output is positive here, seeing the number is 5. So if I change the number to, for example, -1, and I open my terminal again and print pi cs.py, you realize that the number is negative. And if I change the value to from -1 to 0, then we expect to get the value as 0 cs.py, and yes, we have 0 as our outcome, 0. Now guys, section 1.2, we are going to look at advanced data type. So we are going to run this section to the end before we test our codes. And Python provides rich built-in data structures such as mutable, which entail list, dict, set, and byte array, and we have immutable one for tuple, star or string, bytes, and frozen sets. And we also have specialized such as collections, module types. And we can have one example. We start by importing useful classes from the collections module. So from collections, import named tuple, deq, and counter. So we need to remember before we use that named tuple allows creation of tuple subclasses with named field, and deq on the other hand is a double-ended queue that allows fast appends and pops from both ends. And counter on the other hand, it's a dictionary subclass for counting hashable objects. So named tuple, let us have our named tuple example. So let's create a new named tuple type called point with field x and y. So point object will be named tuple. Using named tuple, remember, it's a keyword, and we pass on the point x and y. So now let's create an instance of the point named tuple. So p is equals to point, and we pass on 11, y is equal to 22. So this assigns 11 to x and 22 to y. So if we print p, we expect to get the point to be x is equal to 11 and y is equal to 22. And moving on, we are looking at advanced data type. So I will run this together. So let us access and print the x and y values that we just created using dot notation, like accessing attributes. So dot notation like accessing attributes. So let us print using f string for point coordinate p.x, p.y. The output should be point coordinate 11, 22, and we're looking at deq example. So let's create a deq, which is a double-ended queue with initial elements 1, 2, and 3. So dq is equals to dq 1, 2, 3, and we want to add an element to the left end of the dq. So dq dot append left, and the person 0. Now the dq is 0, 1, 2, and 3. Now if we print the current state of the dq, we will have to get something like dq will be a new value of 0, 1, and 2, 3. And now let us have a counter example. So remember, I would run this together, but you can pause the video and run. Let us create a counter object to count how many times each letter appears in the string. So word count is equals to counter and our, for example, abracadabra, and if we print the count of each letter in the string, we get that. If we say print f string letter count, and then pass on the count word count as our object, we find that A has been repeated 5 times, B 2 times, R 2 times, C 1 times, and D 1 time. So we can try with your name. So let me run these codes collectively and we proceed. So let me run py cs.py. So cs for computer science, and voila, we have our result here. So first of all, the first result is for points. So the output was coordinates 11 and 22. So let me try to expand. So this is the output. Point coordinate 11, 22. This is here, and we also I think we had another point here. So this was the first print statement. This is the reason why I like you typing my codes in VS Code. Sorry, in a notepad before moving here, because of terminal size. So the first print was on line 36, if I'm not wrong. Then this is the output. Point x is equals to 11 and y is equals to 22, and the coordinates, the next stuff is coordinates, where we looked at advanced data type. So this coordinate, so coordinate of p and y using dot notation, we find that 11, 22. And now on dq example, this one, we find that after adding 0 to the left, so we find that it displaced this one and it was added just before 1. So this here on this terminal, and now our dq still the same here that we printed. And now on counting of letters, we find that our word underscore counts is equal to counter. Remember, counter is an inbuilt word from our collection module. So that's why you see it's having some fancy color. So, and we realize that A appeared here. A appeared 5 times. So if we count here, A 1, 3 instances, 4th instance, and 5th instance. That's why you're saying A colon 5, and B appeared twice, 1 and 2, and whereas R the same appeared twice, 1 and 2, and C appeared just 1, and the same way to D appeared once. And part 1.3, let us look at functional programming features. So again, in this section we're going to learn everything, and we're going to run them collectively. So Python supports functional programming paradigms such as first class functions, lambda expressions, map, filter, and reduce functions. We have generators and iterators, and in Python, map, reduce, and filter are built-in functions, though reduce must be imported explicitly from the functools module. So they are often used in functional programming for processing iterable like list in a clean, concise, and expressive way. And let us look at map syntax. It has function and iterable, and it applies a function to every item in the iterable and returns a new iterable, usually a map object, which can be converted to a list. And you can have an example. Remember, if you don't understand well, I have a module on data structures on module number 4. So let us have numbers 1, 2, 3, 4, list of numbers. So this one creates a list of numbers from 1 to 4. And you can have a squares is equal to list map lambda function, and passing the numbers as iterator. So this uses map with a lambda to square each number in the list, and you can print squares, and we're expecting that every number that's 1, 2, 3, and 4 has been squared independently. So, and the resulting list of squares should be 1, 4, 9, and 16. So let us look at filter function syntax. It has function and iterable. So filters are iterable by applying the function and keeping only items where the function returns true. And you can have an example like numbers, or a list of numbers 1 through 5, and want to just take even numbers alone. So list is equals to even is equal to list filter with lambda function and comma numbers as iterator. So if you print even, the output is 2 and 4. So, and also look at the map, or you can look at reduce. So it also has a function and iterable. So it applies a rolling computation to sequential pairs in iterable to reduce it to a single value. So we need to import it first. That is from functools. We need to import reduce, and example on reduce is like from functools. As we said, we need to import reduce, and a list of numbers is equal to 1 through 4. So the product is reduce, and using lambda function x comma y, and it being mapped to x times y numbers, which means that all values will get multiplied, i.e. 1. Okay, I've used 2 asterisks, but you can remove it. So every value will be multiplied, and the output is 24. So let me run and verify the result for all the examples we've done here. If I run py cs.py and I hit enter, you realize that we've got our outputs collectively. So let me go to our first output. Our first output should be let me check here. So our first example was on squares. So if we print squares, the output should be numbers from 1 to 4. So that is okay. Yes, our output starts here. So our output starts here, the number they have highlighted on line number 92. So if we print square, this is what we expected to get. So numbers 1 through 4. And now this one simply means that we use a map function with a lambda to square each number in the list. So this is the function list map lambda x colon x square x star star 2 comma numbers as iterable. So remember we said that the syntax is that it has a function, which means in this case we have a lambda function here, and iterable. Iterable now it's our list of numbers, and the output is what we said about it. And moving ahead on filter function, we say that a list of numbers is 1 through 5, and we want just to have numbers, even numbers alone, using a filter and lambda function. Numbers will be the iterable. So we pass on that this function will evaluate every member of numbers to determine which value is even and which one is not. So we have two members which are completely divisible by 2 without reminders, and they are 2 and 4. That's why we are getting here 2 and 4. And now finally we have reduce function. Remember, reduce applies a rolling computation to sequential pairs in the iterable to reduce it to a single value. So we need to import it first, as we said. So reduce function, and as we said previously, also takes a function function and the iterable. And now, for example, if we use reduce and pass on the lambda function and numbers as iterable, so we are passing on as x comma y colon x times y. So which means that every value within the iterable should be multiplied. So it will be 1 times 2 times 3 times 4, which you get as 24. So that's what reduce does. So reduce is very powerful. So it makes your work easier. So that's why you get in here 24. So guys, before we proceed, let us have a summary table, and we'll have more examples, so don't worry. Summary table showing function, purpose, we have returns, and whether the function requires functools to be used. For example, map function, its purpose is to transform all items, and it is required to return map object, and it does not require functools. On the other hand, filter, its function is to select items meeting a certain condition, and it also returns a filter object, and it does not require functools. On the other hand, reduce, its purpose is to reduce to a single result and single value as returns, and it requires functools. So guys, let us have another example. Numbers again 1 through 5. That's a list, and we're going to look at map and filter functions. Let us have squared of events, and we have a list map lambda being mapped to x squared or x star star, and comma filter lambda to this, and you pass the numbers as the iterable. So this one will create a list of squares of even numbers from the numbers object. So if we print the squared evens, we are expecting to get something like 4, 16. So the only even numbers will be selected or filtered out. And you can use reduce. For example, our product, we need to reduce lambda comma x and pass on the number. So which means we want to calculate the product of all elements in number object using a reduce function. So print the product of numbers and the person the product as placeholder, and the expected output should be the product of each number, and which will be 120. So we shall also run it conclusively, and let us look at generator expression. Again, as using the same number, so gen is equal to x cubed for x in numbers for if x percentage 2 is not equal to 0. So we need to create a generator that yields the cube of each odd number in numbers object. So if we print the cubes of odds and use this syntax list gen, the expected cubes of odds should be 127 and 125. So let me run and I'll get back to you. So here in VS Code, if I can print by ces.py and we get our values as first of all is the squared events. Squared events we get 4 and 16. So we have values here, numbers here. So only even. So 4, 2 will be squared is 4, and 4 is squared will be 16. And now the next value was on the product. So here on reduce. So the product of number, so which will be the product of 4 elements in this list. So which will be product of 1 times 2 times 3 times 4 and times 5. So 1 times 2 is 2. 2 times 3 is 6. 6 times 4 is 24. And 24 times 5 we finally get 120. And now the final example was on cubes of odds. Again, using generator function expression or function. So again, we use the same list of numbers from 1 to 5, and we use this function x cubed for x in numbers if x modular 2 is not equal to 0. So we can still change this one to be 1. So to generate all the cubes for even numbers. So if we print this one, the output is this one, cubes of odd number. Odd numbers here are 1, 3, and 5. So 1 cubed is 1, 3 cubed is 27, and finally 5 cubed we get 25. Great. Guys, let's move to section 2 on computer science theory. So 2.1, we're going to look at computational complexity. And computational complexity is simply a fundamental concept in computer science that's used to evaluate the performance of algorithms. So topics include time complexity, that is how execution time scales with input size, that is measured in big O notation, and space complexity, how memory usage scales with input size. We also look at case analysis, best, average, and worst case scenarios. We also have P versus NP, which is simply an open question about whether every problem whose solution can be verified quickly, that is NP, can also be solved quickly, that is P. And you can have our example. So we can have some definition before having our example. So we have O and bracket 1, it simply means constant time. So when you see that, you simply know that that's the constant time, and it simply means The execution time of the operation does not depend on the input size, and no matter how large or small the input is, it always takes the same amount of time. That's called constant time, and O log n. So logarithm, that's a logarithmic time, and it simply means that the execution time increases slowly as input size increases, and it's usually found in algorithms that cut the problem in half each time, e.g. a binary search. And we have ON notation, which implies linear time. So this simply means that time grows proportionally with input size, and if input doubles, then time roughly doubles. And ON log n notation simply means linearithmic time, and this implies common in efficient sorting algorithms like merge sort or quick sort, and it is a mix of linear and logarithmic growth. And example is sorting a list using merge sort. And you have ON squared notation, which is simply a quadratic time, and it means as time grows exponentially with input. So if input size doubles, the time becomes 4 times longer, and this is seen in nested loops. I have O2 squared n, or raised power n, that is an exponential time, and it's extremely fast growth, and the execution time doubles with each additional input item, and it's often seen in brute force algorithms like naive recursion for Fibonacci numbers. It's time now to look for an example, and def analyze underscore complexity function. So this function represents a demonstration of common time complexities with examples. So it's very long example, so we have to run all of it. So you still remember that O bracket 1 simply means constant time. I can now demonstrate define constant time as with an array argument. So this one will return the first element, and it does not scale with input size. You can also have this. We need to return the R at position 1, or and if R else none. So which means I always return the first item, no matter the list size. And we can have O log notation example, that is logarithmic time. So we have a method or a function def logarithmic underscore time with array and target argument. So this is a binary search that reduces the problem size in half each step. And let us define left right is equal to 0, comma left or len array minus 1. So this initializes such boundaries. So while left is less than or equal to right, so we need to loop until the search space is empty, and mid is equals to left plus right, and divide by 2, which is float division. We need to find the middle index this time, and therefore if R mid is equal to target, this means that if the middle element is the target value, now we need to return true. So return true. And elif if that is not true, r mid less than target. So that is if target is larger, we need to search the right half. So we write left is equal to mid plus 1, or we can write plus 1 is equal to mid. Else, if target is smaller, so we need to search the left half, and right will be mid minus 1, and we need to return false instead, so the target not found. And we can use at O notation, so which is a linear time, array with array and target arguments. So this one will scan the array once to find the target, and we can return the target in R. This one simply checks each element one by one until the target is found or end is reached. And O n log n, that's linear rhythmic time. Of course, we will explain this stuff, so you can pause the video and proceed. The linear logarithmic time with array argument. So this one simply want to merge or quick sort, typically have this complexity, and therefore if length of the array is less than or equal to 1, so this is the base case arrays with zeros or 1 elements are already sorted. So what follows? We need to return the same array, and mid then will be the length of array divided by 2. Remember, that's a flow division also, which means we split the array in exactly half. Left is equal to linear rhythmic underscore time, and we pass the array for all the values from mid and above. So recursively sort the left half, and right is equal to linear rhythmic underscore time are mid and above. So recursively sort the right hand side or right half. So we return the merge left comma right. So this is we need to merge the two sorted half, and we can also define now the merge left right as our helper function for merging the sorts. So we say result is an empty list, so this will hold the merged sorted list, and I is equal to j, which is equal to 0. So this is pointers for left and right lists. So while I is less than length of left and j length is less than length of right, then which means simply means that while neither is list is exhausted, so if length if left I is less than left right j, which means we comparing the current elements in both I and j columns or rows or sides, then we need to append the values. So we need to add a list result.append left, which means add the smaller element to the result. I plus is equal to 1. We move the pointer now in the left list. Else, if that does not hold, then what next? We add the result.append right and the current value of j, which means we add the smaller element now to the result, and j plus is equal to 1. So we increment or remove the pointer in the right list, and result.extend left, so which means add any remaining element now from left list, and result.extend right j colon, which simply means that add any remaining element from right list as well, and you need now to return the result. So return the merged list, and let us look at O n squared, which is quadratic time. So we define our quadratic time function with the array as attributes, and simply this function use cases are in nested loops, as it compares every element with every other. So result will be an empty list as well, which will be meant to store result of pairwise multiplication. And we use for loop for I in R, which means that one will be our outer loop, which will go here through each element, and for J, which is inner loop, will go here through each element again. And what next? We need to result dot append I times J, which means we multiply every pair and add to the result. So return result. This we want to return the final list now, and we can also look at 2 squared n, so exponential time. We can define our exponential time function with n as a parameter, and this is simply a recursive Fibonacci, which means for every slow, it is very slow for large n, and if n is less than or equal to 1, the base case will be fib 0 is equal to 0, fib 1 is equal to 2, and etc. We need to return n, and we need to return exponential time n minus 1 plus exponential time n minus 2. So this recursively computes Fibonacci numbers, and if we print examples of complexity levels defined, this is simply a confirmation that everything is working after those functions. Remember to write everything the way I'm saying, and we can now run the final function to verify the structure. Let's have some values to add to our function. So we print, for example, O1, which is constant time, and we pass on the values 1, 2, and 3. The results will be 1, and we print O log n, which is logarithmic time, with values 1, 3, 5, 7, 9. The result will be true. And if we print On with linear logarithmic with values 1, 3, and 5, and comma 4, that will be at least 1, 2, 5, and 9. And if we print the O notation of log n, n log n, the linear arithmetic time with these values, we're expecting to get the output as this one. And you can also print the O notation of n squared, which is quadratic time, with values 1, 3, and 3, 1, 2, and 3, and the output should be this one, increasing with time. And if we print O notation of 2 squared n, that's exponential time, the result is this. And you can now finally run analyze underscore complexity function, which will execute the outer function and print the message. So this is a very long stuff, so let me try and run in VS Code. So guys, this is our function with everything. So you can pause the video and rewind the coding before running everything. So let me run and check the output pi cs.py. So we have the output here. So let me try. So this is our interest. We started here from line number 72. Examples of complexity levels defined here. So it was just a confirmation message. So, and we want to start with on line number 76, constant time. We have values 1, 2, 3. So despite the number of inputs, the time remains to be constant, which is 1. That's why you're getting this 1 in the terminal. And we have logarithmic time. This one as true, and again O notation or linear time again to be true, which means it's increasing 1, 2, 3, 4, 5, and the result is 1, 2, 5, and 9. So which means it is increasing linearly. 1 plus, we can say that 2 plus 3, 2 plus 3 is 5, and 4 plus 5 is basically 9. So everything's increasing linearly. And we can look also linear rhythmic time. We have 5, 2, 9, and 1. So this is the output. So you can verify all other outputs from your side. Guys, now it's time to look at summary table in terms of time complexity, example operation, and relative speed as n grows. So number 1, we'll start with O bracket 1, and example operation is used in accessing array index, and relative speed is fasted. And O log n, it's used in binary search, and it's very fast in terms of speed. Whereas ON is used in linear scan, and in terms of relative speed is moderate. And ON log n, and it's used in efficient sorting, and in terms of its relative speed it's slower. On the other hand, ON squared can be used in nested loops, and its relative speed is much slower. And O2 raised power n is used in naive recursion, and its relative speed is extremely slower. Guys, now next we are moving to Fibonacci, and remember the Fibonacci sequence is a series of numbers where each number is the sum of the two preceding ones, starting from or 0 and 1. So Fibonacci sequence definition simplified. So f of 0 simply is equal to 0, and f of 1 will be 1, and f of n is fn minus 1 plus fn minus 2 for n greater than or equal to 2. So example of the sequence here, that 0, 1, 1, 2, 3, 5, 8, all the way to 55, and continue. So this is what is the result is, how you get this one, this Fibonacci sequence. So why is Fibonacci a sequence important in computer science and mathematics or any technology world? So it appears in nature, e.g. flower petals, pine cones, shells, among others. It has applications in computer science, mathematics, art, and finance. It is used to demonstrate recursion and dynamic programming in coding programs. And example, we can have an example. So recursive approach, which is simple but slow, exponential time. You can define our Fibonacci function with n as the argument. So, and the base case, so if n is 0 or 1, so we need just to return n, i.e. f of 0 is equal to 0 and f of 1 is equal to 1. And if n is less than or equal to 1, so we just need to return n. So this is the recursive case. We need to return the sum of the two previous Fibonacci numbers. So we need to return the Fibonacci underscore recursive n minus 1 plus Fibonacci underscore recursive n minus 2. And if we print the Fibonacci underscore recursive 6, I'll get the output as 8. So the Fibonacci sequence will be 0, 1, 1, 2, 3, 5, 8, and 8. So i.e. 3 plus 5 is equal to 8. And the iterative approach as well, which entails efficient linear time. So let us define Fibonacci iteration function again with n parameters. So we'll run these things collectively, and a comma b is equal to 0 and 1. So this means that we are initializing the first two Fibonacci numbers, and f of 0 is equal to 0, f of 1 is equal to 1. And for underscore in range n, so we want to loop n times to build up to the nth Fibonacci number. A comma b is equal to b comma a plus b. So we want to update the new a to become old b, and new b now becomes the sum of old a and b, and we want to return a. This simply means that after the loop, a now holds the nth Fibonacci number, and you can print Fibonacci underscore iterative 6, and the output should be 8. That's the Fibonacci sequence 0, 1, 1, 2, 3, and 5, and 8. Let me run this conclusively in VS Code. cs.py. Yes, we find the values as 8 and 8, the way we said. So the first one is Fibonacci. If we print the recursive, the output for value 1 or function 1 is 8. This one, line number 38. This line number 38, we find the output to be 8. And again, the same here, the output to be still the same, 8. Now guys, section 2.2, we're looking at data structures deep dive. So let us look at essential data structures and their implementations. So let us look at array versus linked list. Arrays, in terms of structure, they are contiguous blocks of memory, and access time, they use constant time, that is O1 notation, for indexed access such as R, and we subset as 3. And insertion slash deletion, it's expensive in middle or front, such as ON notation. And use cases, when fast random access and fixed size are needed. For example, static lookup table. And you can look at linked list. And structure wise is that each element node holds data and a reference pointer to the next. And access time is that it uses linear time, ON notation, for indexed access. And Insertion slash deletion, they are efficient at the head or tail or one if pointers are known, and use cases are used when frequent insertions of slash deletions are required and memory efficiency is important. And we can also look at stacks and queues. So stacks, we look at principles. It simply last in, first out. That's the LIFO principle. And operations, you can have a push to add, or pop to remove, and pick to view top. And on implementation is that can use arrays or linked list. And the use cases and in undo operations, backtracking, expressions, passing, function, calls, stacks, among others. And you can look at queues. And the principle wise, they are first in, first out, like in bank system, that's FIFO. And operations like NQ function to add, DQ function to remove, pick to view, front, among others. And variants, which are circular queues, priority queues, the queues, among others. And use cases of include scheduling, buffers, breadth-first search, or BFS, and extract, among others. Hash tables or hash maps follows as our next topic. Structure-wise, there are key value pairs stored using a hash function to compute index. And average case time is that they use constant time or O1 notation for insertion, deletion, and lookup. In worst cases, ON with poor hash function or many collisions. And collision resolution, they use chaining, linked list, or open addressing, probing, among other methods. And use cases they use in dictionaries, caching, symbol tables, databases, indexing, and more. And you can also look at trees, and we'll look at binary trees. Under binary trees, that each node has up to 2 children, left and right, and they're used in hierarchical data representation. And binary search trees, you can look at you have left child, parent, and right child. And the average case operations are O log n notation, and worst case is ON, which is unbalanced tree. And you can look at evil trees, which is self-balancing BSTs, where the height difference between left and right subtrees is less than or equal to 1, and it ensures operations stay close to O log notation, O log n notation. And red black trees follows is another self-balancing BST with red/black node coloring and balancing rules, and it's slightly more relaxed balancing than AVL, but faster insertions/deletions. And the use cases include in search trees, indexes, e.g. databases, B trees, decision making trees, among others. And we also look at graphs, the structure wise that they say they have a set of nodes or vertices and connections or edges. And so let us have an example on linked list. Now let us have example class linked list, and the class node is at that. So this, we are defining the inner class to represent a node in the linked list. So let us have our method with self and data arguments. So self.data is equals to data. So we want to show the data of the node, and self.next is equal to none, which is the pointer to the next node initially set to none. And we also have another method. We define init self with self parameter. So self.head will be equal to none, so which means we initialize the linked list with n nodes, and head is none. And we also define another method, append with self and data, and will be new node will be self.node and person data's argument. So we create a new node with the given data set, and can also use our function here if not self.head. So if the linked list is empty, so head is none, we need to set the new node as the head. So self.head is equal to new underscore node, and you need to return and last is equals to self.head. If the list is not empty, then you need to traverse the last node, and last dot next, so we need to move to the next node until we reach the end, and last will be last dot next, and last dot next will be equal to new node, which will be the link. We link the last node to the new node. And we can also define another method, star method, with self parameter, and this method is used to print the linked list as a string. And we can define some attributes. Node would be an empty list, so, and the current will be self.head, which we start from the head node, and while current, so we need to traverse through each node in the list, and nodes.append star current.data. We need to append the node's data to the list of strings, and current is equals to current dot next. So we move to the next node, and now we return the string representation of the linked list formatted as data 1 is arrow, data 2 arrow, dot dot, and so we return this dot join nodes, and linked list is equal to linked list function. So we're creating a new linked list instance, and linked list dot append 10, so we add 10 to the list, and linked list dot append 20, again we add 20 to the list, and linked list dot append 30, we add 30 to the list, and now we can print our final linked list as link ll, and the expected linked list will be 10, 20, and arrow 30. Now guys, this is our class linked list example, and now it's time to run. So allow me to open my terminal and print the output. Let me enlarge my terminal. File cs.py, and hit enter. So realize our output is 10, arrow 20, arrow 30. The same way we are having this data over here, this one. So we added 10, 20, and 30. So they followed one another in that order. Ten, 20, and 30. Guys, let us look at 2.3 algorithm design paradigms, and we have the following to say that this simply entails common approaches to problem solving, and we have a number of methods like divide and conquer, which entails method dynamic programming using Fibonacci. We have greedy algorithms with digistras and backtracking NQs, as well as randomized Q select. So we can look at dynamic programming for the above approaches, from the above approaches. So dynamic programming, or DP, is a problem solving technique that is used in computer science and mathematics to solve problems by breaking them down into simpler sub-problems, and it is especially useful when the same sub-problems are solved multiple times, and in such cases dynamic programming stores the result of sub-problems, that is memoization, to avoid redundant calculation, thereby improving efficiency. And you can have a code example using Fibonacci sequence as using dynamic programming, that is memoization. So let us have a function Fibonacci with n and mem as an empty dictionary or an empty set. If n in mem, so we want to check the result for the current value of n is already computed and stored. So we need to return the mem n, and if n is less than or equal to 2, so this is base case. The first two Fibonacci numbers are 1, and we return 1. So, and mem n will be Fibonacci n minus 1 comma mem plus Fibonacci n minus 2 comma mem. So this is recursively computed the Fibonacci number and store the result in mem or memon, and you can return the mem n, which returns the computed Fibonacci number for n. And example usage, when you compute the 10th Fibonacci number, so you can print Fibonacci and 10, then we say Fibonacci passing the 10, and the expected output should be 55. If I print by cs.py, I'll get the result as 55 here. Guys, let us move to section 3, which entails system programming. And 3.1, we're going to look at memory management. So, understanding Python's memory model, such as referent counting, garbage collection, or garbage in, garbage out, memory allocation strategies. You have circular references, among others. So memory management and garbage collection in Python in general, we're going to look at memory management definition. So memory management refers to the process of efficiently allocating and deallocating memory in a program. In Python, memory management is handled automatically, but understanding how it works is very essential for avoiding memory leaks and optimizing performance. So Python uses referent counting and garbage collection to manage memory. The referent counting, it is the Python. This is how Python keeps track of the number of references or pointers to an object, and when the reference count drops to 0, meaning no references to the object remain, so the memory is freed. And garbage collection as number 2. So Python's garbage collector is a system for automatically cleaning up memory that is no longer in use, and this happens through referent counting and by periodically looking for objects with circular references, that is, objects that reference each other but are no longer accessible from the program. And you can look at memory management example. So we import system and import gis. Those are inbuilt libraries. So we have memory dem function. We have our list of 1, 2, and 3. So we create a list of list x and assign it to variable y as well. So y is equal to x, which means y now references the same list object as x. And so we want to print the reference count for the object x points to. So if we print the reference count, it will be system dot get ref count x. So the expected reference count should be 3. So we shall run and get to know what's happening. And you can also use post garbage collection to clean up and reference objects. So gc.collect. So this function forces the garbage collector to run, and if we print garbage collection performed and we run our function demo, then let us see what happens. Now let me run by cs.py and we get the reference count as 3, and the garbage collection performed. So this is the statement that we just wanted to be shown, though it is not mandatory. So the reference count is 3 here, line number 40. So which means that the reference count of x, value of x, 1, 2, and 3. So they were garbage out. So let us on section 3.2, we're going to look at concurrent models. So parallel execution approaches. We shall look at threading, input, output, bound task, and multiprocessing, that is CPU bound tasks, and asyncio, that is coroutines and parallel processing. So concurrent in Python. So concurrent is the concept of executing multiple tasks at the same time within a program, and this can be achieved using 1. Threading for lightweight input and output bound tasks, and number 2, we have multiprocessing for CPU bound tasks, and another one, asyncio, is used for asynchronous programming using coroutines. And the following example demonstrates threading, which is the best for input output bound operations like network calls or file reading, where tasks wait for external responses. Concurrency example follows. So let us import the necessary module. So you need to import threading, and this will provide a way to run threads, which is lightweight sub-process, and we can define our threading example function. So this will be the function to demonstrate threading, and define worker with num. So which is the worker function that each thread will run. So we need to print thread and num as a placeholder, executing ... So threads is equal to an empty list, with which is the list to keep track of the thread object, and you can use for loop for I in range 3. So we want to create and start 3 threads at a time, and so t is equal to threading dot thread, and target is equal to worker, comma args is equal to I, comma. So we create a thread to targeting the worker function, and threads dot append t, which means we want to add the thread to the list, and t dot start runs the function. So for t in thread, we want to wait for all the threads to complete, and t dot join, so which means we want again to join the blocks until the thread finishes. So threading example function, so we want to run it to see what is happening, and the expected output will be thread or executing, thread 1 executing, thread 0, and thread 2 is executing. And now it's time now to run them. So these are the expected output that you just seen in Notepad, and you just pasted here. And so it's time now to run them using VS Code terminal. Remember, you can use your own preferred code editor. So cs.py. If I run, you realize that thread 0 executing, thread 1 executing, thread 2 executing. Guys, let us move to section 4, which entail modern applications using Python programming and computer science. For modern application of computer science, it's used one in web development stack and such as full stack development with Python, that is backend using Fast API, Django, Flask, among others, and in front end such as HTML, CSS, JavaScript, Tailwind CSS integration, among others, have RESTful APIs, WebSockets, authentication, that is auth and JWT. And you can have a Fast API example just for demonstration purposes only. So I'll give you all the steps. So Fast API is a modern, fast, high performance web framework for building APIs with Python 3.6 plus based on standard Python type hints, and it is well suited for creating RESTful services and comes with automatic Swagger documentation. And we want to import Fast API class to create the web application. So from Fast API, we need to import Fast API. So we import base module from Pydantic to define the request data models with validation. And from Pydantic, we want to import base model class. So we create a new Fast API instance. So let us have app is equal to Fast API, a function, and we define a data model using Pydantic's base model. So class item, and we pass on the base model name colon string or star, which means that item name as a string, and price colon float, which means the price should be a float or a decimal number. And we can create a post endpoint at the route from /item/. So at app.post/items. So async, we want to define or create a method item colon item, and this will automatically pass and validate the incoming JSON using the item model. So we want to again to return the extracted name and price as a JSON response object. So return, we want to use a curly brace item underscore name colon, it will be item dot name comma item underscore price will be item dot price. And let me give you a hint on how to run this. So how to run this Fast API app. So you need first of all to save the code in a Python file such as main.py. That's just a convention, you can save with your own. So open your terminal and now run the server using uvcon colon or uvcon main colon app hyphen reload. So main simply refers to the file name without .py extension, and app is a Fast API instance. So and hyphen reload auto restarts the server on code changes. So useful, and it's useful during only development process. So you need to open your browser and go to Swagger UI, that's API docs, hit http:// or local server with /docs or redocs with this URL and reload the browser. So we can have this sample request. So don't worry, because I'm going to demonstrate this, but you will have to use it your own data. Name is equal to, for example, laptop. Price will be 9999.99. Sample response will be item laptop, and item price 99.99. So let me demonstrate. However, I will not give the response, but you will have to do it on your own. Let me just demonstrate how to do this. So we have the steps here. We'll be following together. So we have our own codes, but now it's the time to run. Now, guys, I've opened my terminal or VS Code. Now this is our codes in VS Code that we are intending to use Fast API. So we want to set up our projects, and first is that we need to save the code in a file main.py. So but in my case, I saved it as cs.py, and you need to open your terminal the way mine is opened already, and you write this uvcon main:app space hyphen reload. But in my case, I'll have to use cs, then I use uvcon cs, I will use uvcon cs app space hyphen reload. So, and remember, say main will refers to the file name without extension .py. So, and now we need to after the server runs, we need to locate the local server and run. So let us do together. So I will use let me expand my terminal a little bit. I will have to run my program using the steps we've just listed. So I'll start with uvcon cs app space hyphen reload, and hit enter. So it will take some time, and voila, you can see the server is running. Now I will not head to the server. However, it's a challenge to you that you need to move to this URL from your side, and you pass on this data endpoint. So you see that if we try to change anything here, the server loads automatically. For example, if I say again price, you say the server is automatically loading. So, and it has crashed because I am the wrong item. So if I say item, and still the server is back. Yes. Now make sure to pass on these endpoints from your side. So it's time now to move ahead. So you need to visit this URL, and either this or this one to a client. Client means your browser, and pass on these responses. Responses like this. Name will be laptop, price will be, for example, 999.99. We are ready to move ahead. Let me close my server. Guys, on section 4.2, we're going to look at data science pipeline, and we want to look at an end-to-end view of how data flows through a typical data science workflow. So number one is data acquisition. This entails collecting raw data from various sources such as APIs, e.g. Twitter APIs, open weather map. You can also have web scraping, e.g. using Beautiful Soap, Selenium, among other libraries. We have databases using spreadsheets or real-time streams. And number two, after extraction or data acquisition, we have ETL or ELT, extract, transform, load, and extract, transform, or load, extract, load, and transform. And though after extraction of raw data, now we need to do what we transform it by cleaning, normalization, feature engineering, among others. And now we need to load it into a usable format or database. And what follows is data cleaning and wrangling. So with pandas and numpy. And now we handle missing values, fix inconsistencies, drop duplicates, among other methods. We also convert the data formats, standardize values, and more. And now after that we do exploratory data analysis, that is EDA. And under EDA we expect to do descriptive statistics, correlation analysis. We have hypothesis testing, such as using scipy.stats, a stats model, among other methods. And finally we do number 4, we do visualization using matplotlib and seaborn to plot trends, distributions, and relationships. Number 5, now we have to perform machine learning. So machine learning can use scikit-learn for regression, classification, clustering, among other methods. We can now do what you call train and test/split, modeling, tuning, and finally evaluation. And this is a pandas example or data frame summary. So for example, import the pandas and numpy libraries. So we need to import pandas as pd, that's an alias, and import numpy as np. So we need to create a dictionary representing some tabular data. So data is equals to name being mapped to Paul, for example, Henry, and Raul. So the names, they are the names of individuals, and age being mapped to 25, 30, and 35. And these are simply the age for those individuals. And salary, for example, 50,000 USD, 6,000 USD, and 70,000 USD. They are corresponding remuneration salaries. And we can convert the dictionary into a data frame using pandas. So df or data frame is equal to pd.dataframe, and pass on the data. And we can show the basic statistics for numerical columns like age and salary. So print df.describe. So we will print our stuff and see what is happening behind the hood. So this is our data. Again, have a look at it. This is our data, and we want to do print df.describe, which will show the basic statistics of columns like age and salary. So let me enlarge my terminal as I proceed by cs.py, and I run. So yes, our result is out. So we find that age, salary have been displayed here. So we find that they count 3 individuals, and mean age was 30, mean salary as 60,000 USD, standard deviation of age was 5, standard deviation of salary as 10,000 USD, for example, among others. So let's just proceed. Now guys, What df.describe shows as follows. Count, it shows the number of null entries, and mean, that's the average value. Standard, STD, simply stands for standard deviation, which is the measure of spread, and mean slash max, smallest and largest values. 25% slash 50% slash 75% is the percentile distribution quartiles. And we can move on to section 4 of machine learning workflow. So I will not do much here because I have already this module. You can watch in my module number 12. So computer science is in the computer science plays part in machine learning, such as modern ML development, such as data preparation, model training using TensorFlow and PyTorch, model evaluation, model deployment, and model monitoring. Guys, the final section we're going to look at are emerging technologies in computer science. So 5.1 is quantum computing, and introduction to quantum programming entails qubits versus classical bits, quantum gates, we have Qiskit framework, we have hybrid quantum classical algorithm, and 5.2 we can look at blockchain development. Though we have a module on blockchain, that is module number 13, module number 14 to be precise. And we also look at decentralized application development. We have smart contract. We will also have to look at this in the module 14. We have solidity with web3.py. We have cryptography basics, Ethereum, Polygon networks, NFT, and DeFi concepts. So most of these things we're going to look at the module 14 and module 13 and 14. And also 5.3 we have what we call edge computing, or Internet of Things and embedded systems, which has some application like in MicroPython for microcontrollers, sensor data processing, edge artificial intelligence with TensorFlow and light. You have low power optimization, among others. So let us have the summary from our crash course, our computer science crash course with Python. So this is our conclusion and learning part. Let us look at career pathways in computer science. Number 1 is software engineering. You need to master algorithms and system design. You need to learn multiple programming languages to be safe, and you need also to understand software development life cycle. Number 2, we have data science way. We have advanced statistics and linear algebra. You also need to know big data technologies such as Spark, Hadoop, among others. You need also to know domain specialization such as finance, healthcare, and more. And on cybersecurity, we have ethical hacking techniques, we have cryptography principles, we have also security protocols and standards. And number 4, you can also spend your time on research and academia, so as a computer scientist. So this is theoretical computer science, algorithmic breakthroughs. We have also quantum computing research. This is the recommended learning resources to further your studies. On books, you can check out Computer Science Distilled by Wladston, Ferreira, Filho. Another book, The Algorithm Design Manual by Skiena. Another one is Clean Code by Robert C. Martin. We have other online resources or online courses such as MIT OpenCourseWare 6.006 Introduction to Algorithms. You have Stanford Computer Science 229, that is in daily machine learning. You have Harvard CS50 Introduction to Computer Science. In fact, this is the best. I would recommend anyone to use it. And practice platforms that you can use. You have LeetCode, which is algorithmic practice. You have Kaggle for data science competitions, and we also have Code Wars programming challenges. Now this is the end of comprehensive computer science course. Thank you for taking your time to watch, and please don't forget to like, comment, and subscribe to our channel, as well as sharing to our peers. This will support my channel